When we have numerical data, what we want to do is collect some descriptive statistics to help numerically describe what we expect is happening with our data, as well as how it varies. So in terms of expected value, we use the mean. The mean is the average of the data. We calculate this by adding up all the values and then dividing by the number of values that there are. As we move through more calculations and collecting descriptive statistics, we're always going to see two versions for each statistic. So we have this population mean and this sample mean. And what this does is by using different symbols, it tells us where it's coming from. So if we use this symbol right here for population mean, which that symbol is the Greek letter mu. So you say that's mu. So if we use this symbol mu, that's telling us that we calculated an average from population data, meaning we had all of the data from the population, and that's our number. So it's a sign that it's a very powerful value because it took a lot of work to collect all that population data, and it's exact. Whereas if we use our symbol here for sample mean, which how we read that is just x bar, since it's x with a little bar on top, when we use x bar to represent means, that's telling us that we're using sample data. So we collected a sample, took an average, and that's where we got x bar from. So what that tells us is we're going to assume we took a good random sample, so it should be representative of what's happening in the population, but there might be a little error involved. What we're going to be doing is calculating these means by hand, which typically are going to be sample means, since usually with population data, we'll have to use technology to calculate. So to calculate a sample mean, what we do is we add up all the values and divide by the number of values that there are. And this right here, x bar equals, is our formula for calculating a mean. The symbol in the numerator here is sigma, and we're going to be seeing this every now and then with the course. And what it tells us to do is add. It's a summation symbol, and it's telling us to add up different pieces. So in the numerator right here, it's saying summation of x. And what x represents, x is just going to be our data values. So this numerator right here, all this is saying is add up the data values. In the denominator, they use this symbol n, and n is our sample size. So our formula here is just a division of, in the numerator, add up the data values, and then divide by sample size, and that'll calculate our mean. So we're going to go through a few examples so you can see this done by hand, and then in later videos I'll show you how to find this using technology. So for data set A, we have these 5 data values. So if we want to calculate our mean, which we'll assume this is a nice little sample, so we'll use x bar for our symbol. In the numerator, add up 3 plus 8 plus 12 plus 15 plus 18, and then divide by our sample size of 5, because there's 1, 2, 3, 4, 5 data values. So we're going to plug this into the calculator and get a number out. When you do this, plugging into a calculator or using any sort of technology, make sure that numerator stays grouped together. You calculate that addition first and then divide at the end. So we'll get an average of 11.2 out. Same idea with data set B, it's just now we have a little extra value. So 3 plus 8 plus 12 plus 15 plus 18 plus 20. And then we're going to divide by, and now we have 1, 2, 3, 4, 5, 6 data values. And plugging that into the calculator, we should get a 12.6667 out. And just remember to round to 4 decimal places. Then for our last one, what I want us to look at here is this data set that is pretty much identical to data set B, but what's going to change is this last value. Instead of 20, we're going to use 205. So let's see what happens to our mean when we change that one value. So our mean, we're taking 3 plus 8 plus 12 plus 15 plus 18, and then plus this 205. over, and we have 6 data values. And when we plug that into our calculator, we're going to get a mean out of 43.5. So what you'll notice is there's been a big change in our mean. And it's just because of that one data value changing and the fact that it changed to such a large number. What we'll see with data set B is that this is a fairly symmetric distribution. It's roughly symmetric, and when we take that average, we're landing right in the middle there. Data set C, however, is going to be right skewed. We're going to have most of our data on this low end, and then that one data value is way out far in the right tail with that 205. So what that's doing is it's moving our mean, where without that 205, our mean would be over here kind of at the peak of the distribution, but it's moved up because of that large value being added in. So what this shows is that these outliers, these very large numbers, influence the mean. And in terms of representing an average or expected value, it kind of ruins it, in that 43.5 isn't a good estimation of the average of these numbers because one value is really changing that. So for symmetric data, we want to use that mean and standard deviation to describe center and spread of the data. But if our data is skewed, they're not good measurements to use because they're being influenced by those outliers. So standard deviation is something else that we want to calculate. So the mean describes the center of the data where we expect to be. And what we want is a numerical value to describe the spread. Because if we have those two values, that tells us a lot about what's happening with the data because it tells us where we expect to be, but on average, how much that can change by. So what we're going to do is go through kind of a building process of seeing how this formula comes together for a standard deviation. So before making a standard deviation, what we need to realize is what is a deviation. A deviation is just a difference between a data set value and the mean for that data set. So it gives us this distance between the means, or the mean, and data values. So we have our data set here. We're just going to work with a simple set 1, 2, 4, and 5. What we're going to need is the mean for this data set. So if we add up 1, 2, 4, and 5, and then divide by 4, since there's 4 data values, that'll tell us we have this mean of 3. So for deviations, what we want to do is take that data value minus the mean. So for each of these, we're going to take our x value, and what you're going to notice in some books and different websites use this little subscriptive I, just tells us different data values. So we're going to use x1, then x2, then x3, then x4, and then minus the mean. So for our data set, our deviations will look like taking that data value of 1 minus 3, data value of 2 minus that mean of 3, that data value of 4 minus that mean of 3, and data value of 5 minus that mean of 3. So we get these deviations out of -2, -1, 1, and +2. What you'll notice is when I describe deviation, I describe it as the distance between the mean and the data values. However, distance actually isn't a good word to use right there, because what we're going to see here is that we get positive and negative values out. And that's going to cause an issue that we're going to have to fix in a second. But to get to the definition of a standard deviation is the average distance away from the mean. So we want to get an idea of how are the individual data values differing from the mean on average. And I just want to draw a quick little dot plot of our data and seeing how the mean relates to them. So going 1, 2, 3, 4, 5 for our number line. And then we'll have a dot above 1 for data value of 1, 2, 4, and 5. And our mean of 3 is landing right in the middle here. At 3 is our mean. So with finding this standard deviation, we want this average distance away. So how are these individual data values differing from that mean? But in terms of average distance away, distance should always be positive. in that if we look at 1 and 5 and how they differ from the mean, they differ equally. 1 is 2 units away from the mean, so is 5. So where we run into an issue is with our deviations is that positive and negative is coming out, and we only want positive values. We want to see that 1 is just as far away from 3 as 5 is. But right now they have two different values of -2 and +2. So because negative distances don't exist, we look at the squares of the distances. So instead of just deviations, something we're going to have to evaluate are the squared deviations. So where we took these differences of the data values minus the mean, now what we're going to do is just square them. So where we had 1 minus 3 before, we're going to square that. And 2 minus 3 squared, 4 minus 3 squared, 5 minus 3 squared. So now our values coming out will have a +4, +1, +1, +4. And now we can see exactly what we wanted, where how 1 differs from the mean, giving that value of 4, is just as equal as how 5 is differing from the mean, where it's also giving out a 4 right there. So this is getting at distances away from the mean. Technically right now we have squared distances away from the mean, but we'll take care of that at the end. What we want to do is take an average. But when you take an average here, instead of just dividing by the sample size, it's going to be a little different. Instead, what we do is we divide by the sample size minus 1, and this is because we have to use something called degrees of freedom. It has to do with the fact that we're using sample data, and when we have sample data, there's a little error involved, so we have to adjust our sample size to kind of make up for that error. So degrees of freedom, we're using sample size minus 1. So in our numerator for taking an average, we're going to add up these squared deviations, and in the denominator, sample size minus 1. And that calculation right there is called variance. So variance has two notations to it, just like the mean did. Variance, if it's coming from a population, we use, it's a little circle with like a little tail on top. That's called sigma, and we square sigma. So sigma squared, this is our population variance. Then, for if it's coming from a sample, we use S squared, and that is our sample variance. So again, it just depends on what kind of data we have, and that tells us which symbol to use. So for us, calculating sample variance, what we're doing in the numerator is we are adding up. So I'm going to use that sigma symbol to represent addition. And we're adding up these square deviations. So in parentheses, we're taking each data value, so each x value, minus the mean, so minus each x bar value, and squaring it. So adding up deviation squared, and then dividing by sample size minus 1, or n minus 1. So in our calculation for variance, in the long form of what we did through these steps here, in the numerator, we'd have this 1 minus 3 squared, plus 2 minus 3 squared, plus 4 minus 3 squared, plus 5 minus 3 squared to make up that numerator. And then the denominator, we have 4 data values, so we have a sample size of 4, and then we're just going to subtract by 1. And if we throw this into a calculator, this would give us a fraction with a numerator of 10, denominator of 3, which would round to a 3.3333. So this 3.3333, that is our variance. Variance is just kind of a stepping stone to standard deviation. There are ways to use it, but typically we're more interested in standard deviation. Because right now, if you think about if we had units here, like if we were talking about age in years, and we had a data value of 1 year, 2 year, 4 years, 5 years, since we squared at one point, our units for this 3.3333 is actually years squared, which doesn't make much sense. So that's where we need this extra step to get to standard deviation that just requires taking a square root. So standard deviation for the notation will have the same population and sample scenario, and we just take those symbols for variance and we just remove that square symbol because we're taking the square root. So for population standard deviation, it's just sigma for the population value, and then just S for sample standard deviation. And what we do is, for our formula, you take that formula for variance, so in the numerator, adding up those deviations squared, and dividing by sample size minus 1, and all we need to add in there is a big square root symbol over everything. So for us, where we got that 10/3 out, for standard deviation, we need to take the square root of that 10/3. So our standard deviation for this example would be 1.8257. So that's how the formula comes together for standard deviation. We kind of get to variance, and then once we take the square root, that gives us our standard deviation. So let's practice. We're going to go back to data set A, so that 3, 8, 12, 15, and 18. And for that set, we found that there was a mean of 11.2. And what we want to do is calculate that standard deviation. So, standard deviation, what we can start with is there's going to be a big square root symbol. So you can just draw a big square root symbol. Then we're going to have our numerator and denominator. In the numerator, we're going to take each data value minus that mean and square it. So 3 minus 11.2, square that, plus 8 minus 11.2, square that, 12 minus 11.2 squared, plus 15 minus 11.2 squared, plus, and for the very last one, 18 minus 11.2 squared. So all of that goes in the numerator. Then the denominator, we take our sample size, which there are 5 data values, minus 1. If you get nervous about plugging this in all at once into the calculator, what you could do is separate, so we have our square root, and just calculate the numerator. Calculate that part on its own, which would be 138.8, and then divide by 5 minus 1, which would be 4. And this is a little easier to plug into your calculator. And that would be a 5.8907. Throughout your work, like with your mean and with calculating that numerator, if you're doing any rounding, just be sure to stay to 4 decimal places to keep a good level of accuracy. If you round too much, it can really affect your end result. So last thing we want to do is, how do we interpret mean and standard deviation? So using this data set A, let's say these were representing ages of 5 randomly selected people that are visiting the Oregon Zoo. Describing the center and spread for this data, now we can have units attached. If it's age, it's that these numbers are in years. So the mean is our expected value. So for people visiting the Oregon Zoo, we expect an age of 11.2 years old. When you're making your sentences, feel free to round how you see fit. Like if you interpreted that as 11 years old, just be sure to throw in the word about in there, but that would be fine. But in your actual calculation work, we want to see those rounded values. Then the standard deviation tells us how this differs on average. So we expect an age of 11.2 years old, and this differs by 5.8907 years on average. So what this does is it gives us an idea of what we expect to happen and how we expect it to differ. So while we expect 11.2 years old, being below by about 6 years or above by about 6 years is kind of expected too.